Okay, so the bell ringer usually today, I'll set it up. I will make a video of it separately, so if you want to watch that a little bit later on. And then we'll just go into the back half of today, which is important moving forward. So I'll set it up so you know, okay? What I usually do is something to the effect of this. I usually say, hey, some sports ball is on the ground. Pick a sport.
Football.
Football. Okay, well, I didn't do football really well, so we'll do football. Agreed. So, give me a speed that the football is hit at.
4 meters per second.
I think you can do better with the kick.
24 meters a second.
Let's go 20 meters a second it is. Okay, and give me an angle that sports ball is hit at.
55.
Okay, now, when you do these, I hear you. Notice the way I set up this picture. Now, one thing that I found that students have a habit of doing is whenever we start to go up at an angle, they always draw it at 45. What I regularly suggest is this. If it is above 45, make sure that you don't have to be perfect, but make sure your sketch is obviously above 45. And in this particular case, you can see it's obviously below 45, so pick an angle lower than 45. 30. I heard 30. All right. So 30 degrees. The next question that I would ask is simply, how high does the ball go? And how far does the ball go? These are two separate questions, and I want to point out that technically it's looking at two different locations. How high the ball is going to go there. How far the ball goes over here. Since it is two separate locations, two different times, two different final velocities, these technically revolve around two different sets of variables. When you solve these problems on a test, on a lab, you require two sets of variables. And I use the word technically because most of that set of variables you'll find is exactly the same as it was before. As a matter of fact, I'm just going to go. I usually let you do the problems. I'm going to see what I can do about doing this kind of quick here. What should I do first to fill out my set of variables?
Given.
Right. I'm sorry. Within the what is given? Give me any givens.
Initial velocity. I was thinking beyond.
Okay.
Trying to make it one word.
And Y.
Okay. What's the velocity initial net?
20 meters per second.
Nope.
Initial velocity.
What?
No, it's not. No, it's not 20. It would be 20 if it was shot straight.
Oh, we gotta solve the cosines.
I already
You
got
did Y. Yeah. Yes. In other words, what are we doing in order to figure out velocity? Trig.
My bad. I forgot we were doing.
Ultimately, if you have a vector in polar form, which this is, polar meaning I've got magnitude and angle, they must turn into components before you can ever do 2D kinematics. So, in other words, we've got to take this component, velocity in the x, and this component, velocity in the y, and the only way to do that is trig. So somewhere to the side, I'm going to do that work. How do I calculate velocity in the x? Just do the math so that everybody can see it. What you got? What would I write out?
20 times the sine. 10 times the square.
Cosine.
Oh, we're trying to find the x.
Okay. And then the y, of course, would be
20 times sine.
yes. Now, Wes was about to point out that this is a 30, 60, 90. There may be a reason that I attached to the 30 degrees that I heard so quickly right there, because since that is a simple triangle, we know that the y component is half of whatever that is. So that means and you can do this, you can just punch in your calculator, of course, but it would tell you that this is 10 meters per second y hat. And then the x should be 17.2, if I'm not mistaken. 17.32. I was off. I feel embarrassed.
Even Tony Stark as well.
17.32 x hat.
Yeah.
All right, what else do we know?
Gravity, negative g, and the y.
And along with that,
0 in that.
and see previous conversation where I mentioned that technically you're doing trig here too, right? You're just taking 9.8 cosine of 270, 9.8 sine of 270, but we don't really need to do trig to see it's all in the negative at y and none of it's in the x. Okay, so if let's pick which one you want me to do first, range or height.
So if we're trying to find out how high it goes,
So let's start with let's set height then. Okay.
Yeah.
So what other variable would you set? VF and the y is
0.
now make sure it's specifically in the y. Now notice something very important though, and What are we solving for if I said max height? So actually, if you look at this setup, do we even need the x actually? No. The main thing to keep in mind that separates this from 1D kinematics is simply that it's not going 20 meters per second up, it's going 10. We would have had to split it up. So here I go. I'm going to use this equation right here. Okay? And don't plug in zeros unless they cancel. Do we have any zeros? Yep. So that goes to 0. I'm going to subtract that term, divide 2a, and that's going to get me delta y. Will the squared cancel that negative? Will the squared cancel that negative? Nope. Because? Nope. Because the negative's not inside, the VIY is being squared, negative's not in there. Also, this negative will cancel with the negative that is right down here. Eventually, it doesn't cancel because of the squared. So 10 squared is 100, divided by 2 is 50, divided by 9.8 is roughly 5 and change. Someone calculate the exact for me. What you got?
I got you. My calc is on E.
You guys, we are just doing the bell ringer for today. What you got? 5.1? Yep. 5.1 meters in the air. Now, I'm going to switch colors here. I am recording, by the way, those of you guys that just came in, so if you want to catch the earlier part, you can certainly get that. The question on the table, so you can get the back half here, is we've hit sports ball in the air, 20 meters per second at 30 degrees. The first question was how high does it go? We just answered that. That's 5 meters. And the new question is how far does it go? Okay. Now, let's run back. Now, usually, like I said, if this is a test, if this is a lab, you just need to set up a new set of variables. Either go somewhere else, write it down again. But the good news is, and I'm going to use this to show this, a lot of these variables are going to be remarkably the same. Will VI be any different for this second set? Absolutely not. What about VF?
No.
Yes, it will.
Final velocity.
Will final velocity be 0 when it hits the ground?
No.
No. Which way will it be going when it hits the ground?
Forward.
Negative.
Or down.
Negative. Right, but specifically in the Y, it will be going
Fourth quadrant.
down. So we don't know what this is. Now, those of you that might recognize the symmetry of this situation might be able to go, yes, we do. Yeah, I know. But calculation-wise, stuff ahead of time, we don't. Should acceleration be any different?
Nay.
No. So, what will be different? What variable can I set such that I can calculate the maximum range? Yes.
VI.
No, we have VI. There's one other variable we're going to need in order to solve this
Time.
problem. Sure, but we don't know what delta time is, right? We know delta y. It started on the ground, yes?
Yeah.
And it ended on the ground. So is its total displacement 0?
Yeah. For Y.
For the y, it is. In the y, basically, if I drew delta s right now, it would start here and end there. How much of that's in the y? None of it. Delta y is 0. Now, does that mean it didn't move in the y? Nope, but displacement stands for the change in position. Has the position in the y changed from the beginning to the end? No. And so, this right here is 0. Now, our solution to the rest of this problem is remarkably similar to what we have done before, with one small, simple thing different, so I'll cover that in just a second. But ultimately, what are we going to try to find in the y? In the y-axis, we're going to find time. And what are we actually looking for here?
Displacement.
In the x. We're looking for delta x. So, we're going to solve for this guy first. So, the equation that I would use here is this one. Now I know that this equation gives some people PTSD. Because, oh crap, we're going to have to use quadratic. But I'll remind you that actually we don't have to use quadratic here due to the fact that one of the variables cancels. What variable cancels?
Would it perhaps
Yeah.
be delta of y?
It's delta y. Right there. Now, why does that make my life easier? Well, now, because delta y cancels, what simplification can I do? I can divide everything by delta t. Why couldn't I divide by delta t if delta y was here?
Because it would be divided, because delta y would be divided
Yeah.
by delta.
Students get in this bad habit of thinking it's I divide on the left and the right, both sides. No, 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 it's not dividing both sides, it's dividing every single term. So now we can divide by every term because that's 0. So if I divide this by delta t, that cancels. Divide this by delta t, that cancels. And 0 divided by delta t is just 0, so it doesn't give us anything new. So what do I have now? I have 0 equals VIY plus 1/2 a delta t.
So negative VIY
Negative VIY
times 2
times 2.
divided by n equals delta t.
Very good. And negative 2, what was VIY?
10 meters per second.
Good call.
And of course, acceleration is
Negative g or
negative g. And you'll notice the negatives cancel like they're supposed to. That's going to be 20 divided by 9.8, which is going to be 2 and change. Probably 2.1-ish.
2.04.
Whoever came up with kinematics has to be a genius. Because how do you know that those variables equal that one
We
thing?
did it.
I know, but like
We specifically did the lab to show you exactly what you're saying right now.
oh I know, but like it's still so crazy that like the math rules.
It's more crazy though, like the people who come up with like the quadratic formula.
I don't like thinking that the math knows.
Like, that's
Well,
the best.
okay, couple things to that end. Number one, keep in mind that when you learn in a class like this, it is a little bit. I'm shortcutting most of physics, right? From the beginning of this class to the end of this class, we're essentially covering 400 years of what some of the smartest individuals across all of the earth figured out slowly and trial by error. And ultimately, you have to keep that in mind. How do you figure stuff out? You do the work, trial and error. Do you think the first day they did this, they came in here and just, no, absolutely not. Plus the fact you got to keep in mind that kinematics has been slowly developed over time, and actually the way I'm teaching you is not the way it was originally learned, it's just the easiest way to learn the content. All right, moving on. So, question was, what's delta x? The rest of this problem is pretty easy, because what is velocity in the x? What's velocity in the x?
17.3.
17.3 meters per second x hat times 2.03 seconds, so roughly 34.6, a little bit and change. Let's go with 34.8. I don't know. Let's see what you got.
Okay.
Nick, you all right, champ?
Yeah.
Cool. What do you get? Not you specifically. I can't even tell you. What did we get?
15.3.
No. 17.3 times 2 is definitely not
I did
15.3.
17 minus 2.
35.3 sounds right.
That's what I got, yeah.
Balance is off the dumb piece too.
So this would be a soccer ball. Just so you have clarification, the soccer ball is launched at 20 meters per second, 30 miles an hour, a very reasonable thing. This is going probably about 40 yards down the field. This is a solid kick, absolutely a solid kick. And of course, they could have got a little bit more distance out of it by hitting it at what angle?
45.
Would have been a
That's
better bet.
not true. When you're kicking the ball,
It's
not
100%
always true. Well, in this scenario, yes, it is. But when I'm kicking the ball, it's not true.
It's true.
Why?
Oh wait, no, I'm thinking about the angle.
Let's do
to
this.
kick it
true.
over the field goal
Some math
post.
there.
Okay. All right.
That-
Now, we made this yesterday. I certainly make mistakes. Okay. I'm not beyond fallibility or whatever. But that being said, in this case, no, it's 100% and 10% true.
I was thinking about the angle I have to kick it to make it over a field goal post at the most top.
What angle?
That is a different angle for an entirely different host of reasons. But if you are a football player right now, because a bunch of them apparently can hit 60-yarders with ease, they are hitting it close to 45 as much as possible to get the max range out of that ball. But keeping in mind they're not trying to get it to the ground, they are trying to get it up in the air, so there's a slightly different blah, blah, blah. Moving on. All right, so today's problem is started right here.
Mark Cuban has a great video about kicking.
Not enough time. Well, we ran out of time today. This usually fits in like 20 minutes.
I wasn't that nervous because if I get get too nervous, it would suck. I know you do it. It's just the more you make out of it, you know, I know the physics and I know that it makes sense. So
Okay, he said physics. I'm moving on. Let's talk about the physics that goes with this. They said that the car was a 171-foot jump.
I'm sorry.
Now, here's the thing. When I was younger, I used to think very foolishly, or maybe not so foolishly. I used to think that if people wanted to make a big jump, here's what they did. Took the gas, they slammed it into the floor as much as possible, and went as fast as they possibly could. Okay? Now, given the conversation that we had yesterday, that's not necessarily a great idea. Because here's the deal. They're going to leave with some velocity. We'll call this velocity total. Now that velocity corresponds, as we mentioned yesterday, to a very specific path. Now, obviously I want to go fast enough. I want to definitely be able to make it here. 171 foot. But why is it probably just as dangerous to put the gas down as fast as I can? What would be the problem with going too fast?
You wouldn't get any, like, because, like, you'd be going too fast and the car would hit the ramp weird and then you go up.
Nope.
Like,
No, it's not nothing that. It's straight up. You hit it normally. There's no issues with that, Jack. What's the problem with overshooting it? The x and the y variables are kept completely independent of one another. Would you be okay being strapped to a car right up here and just being let go? You saw how high he went, right? Would it be okay for your shocks in your car? Or the shocks in you, aka your spine? Would your spine probably be okay if we just let you go from about a 4-story drop in a car and just slam directly into the ground? Probably not feeling great for a few weeks, yes? So, that means that more than likely in his car, I don't know this for sure, but more than likely in his car, there was definitely on the speedometer a piece of tape, and it said, hey dummy, go this fast. Definitely go this fast. That speed would have corresponded to here. But there was more than likely another piece of tape, okay, right up here that said, hey dummy, don't go faster than this. And that speed probably is corresponded to right here. You'll notice that he actually perfectly landed about the middle of the ramp, so probably right in the middle of those two respective speeds to be able to cruise down. What we are going to do today is we are going to do the math to figure out what one of those pieces of tape was. What was the speed that corresponded to this, the minimum spot right here? Now, yesterday I told you something in the baseball problem. Don't want to have to compete for conversation, please. Especially not in a collegiate level physics class. All right. We're going to try to figure out what speed it has to go to land right here. And like I said, yesterday, I told you that there is we didn't want to put the delta x and the delta y in because I told you we don't know that the object is going to go through that specific spot. Yes?
Yeah.
However, today, do we want the object to go through that specific spot? Yeah, so we should be able to set both the x and the y. Let's start doing that first. So let's come over here. I'll set up all of my variables real quick. And let's begin with the delta x and the delta y. Okay? Just a gentle reminder, 3.28 feet is 1 meter. Take about 30 seconds to calculate both delta x and delta y. For these guys coming back late, this is recording right now. So we will have this video, both the bell ringer as well as this problem on that video.
You said the delta x and y.
Mm-hmm.
Yeah.
Don't say anything dumb for the recording.
Like that, yeah. Don't do that. All right, 171 feet should be pretty easy. You've calculated it, yes. How far is it?
Oh, wait, I got you.
52.1 meters, very good. And given the general pictorial look of this and the bell ringer today, what is delta y? Zero.
Yeah.
Why is it? Because this ramp appears to be the exact same height as that ramp, and therefore delta y should be 0. Now, I do need to give one more piece of information, just one more. Sadly, not a lot. I'm going to tell you that the angle of this guy is 20 degrees. Okay, let's come back over here. What is the other easy thing we can knock out?
Gravity.
Acceleration in the y is,
Negative g.
and acceleration in the x is.
Zero.
Cool. See previous conversation. Now here's where it gets a little bit tricky, because we don't have any other information that we can fill in. We don't know how long it's in the air. We definitely don't know what speed it's going to land, and we're trying to figure out how fast it's leaving, so we don't necessarily have Vx or Vy. But let's come back over here, and I'm going to draw this guy up here and ask this. Pretend for a second you knew what Vt was. If you did, how would you calculate velocity in the x?
Cosine.
Cosine. You whatever that number is times the cosine, right? So let's come over here. I'm going to say that Vix is Vt
Cosine.
times the cosine of 20 degrees. And for the y, then that would be
Same thing with sine.
And now we actually have all the information that we can possibly get of here. But here's the issue. That's a variable, so do I actually know that number?
No.
No. I need 3 pieces over here on the y side. Do I have 3 pieces?
Almost.
But no.
Yeah.
Okay, how many? I need 2 pieces over here, yes?
Yeah.
Do I have 2?
You do.
Do I know
Yeah,
Vx?
Oh no. Because
Remember, 0 doesn't technically count
Yeah.
because this is a constant velocity. This is Vx equals, delta x equals Vx times time. We have delta x, that's it.
Yeah.
So we don't have enough information on either side. What did we do last chapter when we did not have enough information?
Now that's coming together.
We're going to have to do multiple equations, multiple unknowns. Now, I told you guys last chapter that this was not going to be required last chapter. Haha, welcome to the next one. It's 100% required. You're going to be doing this on both the test as well as also on the lab starting tomorrow. Now, the good news about this problem is, as complicated as it is, a lot of these are the most plug and chug I do in this, meaning if you can kind of follow the moves on how they go, it's really just going to be changing the numbers slightly in the various situations. So just try to follow as best as you can. So here we go. I need to do multiple equations, multiple unknowns. Now the y side has 4 possible equations, so I don't want to start there. How many possible equations could I have for the x? Just the one, so let's begin there because it has to be that one. So I'm going to write out delta x equals Vx times delta t. And I don't usually like to plug in, you know this, but that being said, it's complicated, so let's go ahead and fill in as much as we can. What's delta x?
52.1.
52.1 meters x hat. All right. What is Vx?
We don't know. Oh well.
Right, what we do know.
V.
Vt cosine 20. And do we know delta t?
No.
No. Now here's the nice thing about what we just did. We have an equation. Do we also know exactly what our unknowns need to be?
Yeah.
Yes, we have 2 unknowns. If you have 2 unknowns, what's required to solve it?
Unknowns, 2 equations.
2 equations with the exact same 2 unknowns. Now, I know it's going to look messy, but I just want to give you guys a heads up. If I gave you this instead, if I said x, hold on. Come on. Yeah, let's do this actually. X equals 0.8 times y times 4 is equal to 3y plus x equals 12. All of you pretty sure that you could solve that pretty easily.
Yeah.
So that means you can do what I'm about to show very easily. Okay? The only thing that's an issue is the fact that math uses x and y so often that you're just grown so accustomed to them that you're more used to them than anything. But quite frankly, this first equation, is that equation right over there. They're basically identical in that particular respect. So what we need now is another equation with the same 2 unknowns. So I'm going to go over to the y side. Given that we have to have the same 2 unknowns, what variables must be in this new equation? Oh, so Vy has to be in there, and delta t. Now I've got the 2 variables in there now. Do I want any more variables? Ideally, no. So I should probably try to choose things that we know for everything else. Yes?
Yeah.
So I want to choose this guy and this guy. Have I now selected 4 variables?
Yes.
Cool. So that means there is an equation that goes with this. What equation goes with this? Agreed. I know it. What is it? Trying to use our brains. Here we go. We got this.
Is it the delta t squared?
It's the which one?
Delta
Plus
t
1 half
squared?
a delta t.
Read the whole thing. What's that?
Delta y equals vi. Delta t.
Oh,
plus
hold
1
on.
half
You're
a
missing.
delta
You're
t
missing a
squared.
piece there.
Vi y.
Thank you.
Delta t plus 1 half a delta t squared. A y delta t squared.
You're right. Technically, it is a y. Like I've said before, you'll notice me I'm regularly dropping the y on the a because it is only accelerating in the a, but sure. All right. Now, let's go ahead and plug in some more.
Okay.
What is delta y? 0. Okay. What's VIY?
Vt times the sine of 20 degrees.
Okay. And now we got delta t, which we don't know. Do we know a? What is it? Negative g, or negative 9.8. And we don't know delta t squared. Now, good news, bad news. Okay? The good news is, like I said, you guys know how to do the system of equations. The hard piece of this is just putting it into action, making sure that you can get 2 equations with the exact same 2 unknowns. The other good news is this. This right here, if you are capable of doing this and setting up those 2 equations on any, it's going to be worth about 70-80% of the points on a test. The math that I'm about to show you in a second is a small modicum of how many points. Now, obviously, I want you to be able to do it well. Obviously, moving forward into greater physics, sure, I need you to be doing a system of equations. But I just want to highlight that if you can get here, you've done the physics. You have done the physics. We're now heading into math. Yes, the math gets a little bit icky, but ultimately, this is what I need you to be able to do. Give me a fist of 5, your ability to replicate this. Okay, so that means you guys understand the new stuff. Okay, and what I'm about to show you is just system of equations, albeit it does look a little bit complicated. It's still just system of equations. What are the 2 methods of solving a system that looks like this?
Substitution.
And what's the other one? The E way.
Elimination.
Elimination. Now, elimination is almost never used. There are some spots where it's very valuable to use. You'll see them in here. We'll talk about them when it happens, but ultimately you can pretty much lean straight into it's probably going to be substitution. So if you had to solve this system of equations, what would you do? What would you do right now? Just generally, you have to do it. Just you solve for one of them, right?
Yeah.
So solve for you could. So actually, this is already solved for. My apologies. So it's already solved for. Well, we'd solve for one, substitute into the other. So what are we going to do here? There you go. Now, I'm going to tell you the simple way to do this real quick, okay? It's not going to get us directly to the answer, but it's actually pretty easy, and it's this. We're going to start with the simpler one up here, okay? I'm also going to remind myself that cosine of 20, as complicated as that looks, is just actually a constant. It's a number. You could punch in cosine of 20 and even just put that constant in the math if that makes it a little bit simpler. Now, I don't suggest that because I'll show you another simplification that we're going to do in just a second, but it is just a number. So I'm going to take this guy and I'm going to solve it for either Vt or delta t. Tell me which one's going to make your life easier.
Delta t.
No.
Oh, sorry.
Here's why. Let's just play this out why so you can see it. Why is solving for delta t not going to make your life easier when you come down here?
He's got delta t and delta t squared.
Well, number 1, you're going to have to substitute it in twice, and number 2, yep, you're going to have to square everything inside of it. That's going to make it a little icky. Now, you certainly could. That would make your life easier, and that we would just get Vt and then have the final answer, but that's not the easiest mathematically, so let's go ahead and solve for Vt. What simple thing should I do to solve for Vt here?
Divide.
Yes, divide by those 2 things, right? These are both just separate numbers. So Vt is going to equal 52.1 meters x hat over cosine of 20 degrees times delta t.
Oh, wow. I'm starting to see something come.
Sweet. All right, now what do I do? I've isolated Vt. What should I do next?
The same on the bottom.
Nope.
Oh, something multiply that.
What's the process called?
Substitution.
What should I probably do?
Substitution.
Okay, so I'm going to rewrite this equation, substituting in that VT for this VT right here. Okay, so this is I'm going to write that VT first, just so I can get that out of the way. Now, you probably are not going to have separate colors, although you're welcome to them on my tests. You're probably not going to have different colors to do this, but I would highly suggest, if nothing else, put parentheses around this so you can make sure to notice that that is just that VT right there. Everything else I'm going to put back in blue so you can see that I've just substituted in that part. So that's just VT. So a lot of times when people put this complicated in thing for VT, they've written so much that they forget this part. But this should also be times the sine of 20 degrees delta t. And I'm also just going to, I don't have to plug anything in here, but I'm just going to move that negative from the negative g up here. So it's negative 1/2 g delta t squared. And as icky as that is, all we have left to do is solve for delta t. And there is a nice simplification, or a couple of simplifications that we can use. What's the first simplification that you can see in this equation that'll make our lives easier?
Quadratic form.
No.
Divided by delta t.
The delta t is right here in the middle. There's one on top and one on bottom. So those will cancel.
Ah, good.
The next simplification you don't have to use, but I think it's helpful to know. What is the sine of an angle?
The ratio.
What is that ratio?
Of a triangle.
Thank you. Opposite over hypotenuse.
That was like
And what is the cosine of an angle?
adjacent.
So you'll notice if I take specifically sine on top and divide by cosine, that would be opposite over hypotenuse over adjacent over hypotenuse. And if I simplify that complex fraction,
You get tan.
you will 100% end up with tangent. That is opposite over adjacent. So as long as they are the same angle, since you see sine on top here and cosine on bottom, that actually simplifies. So this whole middle term simplifies out to 52.1 meters tangent of 20 degrees.
What if you get cosine over sine?
It's 1 over 10. Or cosine if you prefer. But I would, a lot of times I just leave it the way it is. Doesn't matter. Okay, and then that would be minus this guy right here. And we're trying to find t squared. No, we don't have to do quadratic because there's only one t term here. So this is actually, again, as messy as it looks, just simple algebra. We need to isolate the t and solve for it. So what do I need to do to isolate the t?
Divide.
Disagree.
Wait.
When you move terms around, you know what I mean by a term. Term is always added and subtracted. So what do we need to do to get t by itself?
5.2.1.
You can do one of two things. You can either subtract this term on both sides and then cancel the negatives afterwards, or add this term on both sides. That's what I would probably prefer because I'm going to use the whiteboard. What's that? Because I made a mistake.
I noticed that.
Cool.
That was his fault.
See something.
Because I'm trying to go quickly here. All right. Now what do I do to get t by itself?
Multiplied by 2g.
Okay. Then
Then square root.
oh, you're missing something.
Oh, what am I missing?
You gotta divide out delta t squared again.
Nope.
Go to square root.
Nope.
No,
Divide by
G.
Divide by g. Multiply by 2. Divide by g. Now you can square root it, and that will get you time.
Oh.
Just go ahead and calculate that for me, please. We're almost out of time here, guys. Let's hustle up, please. Make sure that you've got this work down. If you, for some reason, foolishly did not write this work down today, please make sure that you watch the video so that you can get it down. If you're on the video right now, what were you being a fool for? Why did you not, I don't understand. You're in advanced physics class. Why are you not writing stuff down? That doesn't make any sense to me.
Silly
I agree.
I got 1.96.
Yes! Okay, rounded 1.97. All right, now, that is not the final answer, though. Be careful when you do all this complicated work. Remember to go back and ask, did I answer the question? What was the question?
Not time.
What was the question?
Oh, I don't remember.
Asking if it can make it over the jump.
What was the speed that you would have to do to pull this off? So what did we technically just calculate?
Time in X and
Specific,
Y.
yes, I know it's time. Specifically what? Yes, the time it took to go from that location to that location right there. Now, it's not invaluable piece. If you go back and watch the video, you will see he's up there for about 2 seconds. But let me ask you this. If you had solved for X on this, what very simple thing would you do to solve for Y? You would plug in that Y, plug in that X, and calculate Y. So here's what we're going to do. We're going to come right over here to where we already solved for VT and simply just plug in delta T. So 52.1 meters x hat over cosine of 20 degrees times 1.97 seconds. How fast does the car have to go? I believe it is, I'll do it for you real quick. Oops, divide.
I'm going to watch the video on the last
Cosine of 20 divided by 1.97. 28.1 meters per second.
Oh, wait,
In other
I
words,
understand now.
he has to be traveling 63 miles an hour. Now, you watched the video. Was he traveling 63 miles an hour below or above? Why do we know it's above? 63 miles an hour is directly associated with, yes, the minimum right here. Since he landed right over here, he was probably going a little bit faster than that. Of course, if you had wanted to calculate the speed for this guy, you would just need to know that delta X and that delta Y and plug them in instead and do that work again.
That was good.